this lecture of the heat equation. In this lecture, I will solve the questions related to the heat equations. Let us consider the first type of question, type 1, when the ends of the bar are maintained at 0 degree centigrade. Let us consider this case when your ends of the bar are maintained at 0 degree centigrade. So let us start with question number 1, and in this question I will try to solve 3 questions with the help of the same logic. So consider a rod of length L. A rod of length L with insulated sides is initially at a uniform temperature . Now I am solving 3 questions. In the first question, my initial temperature is, say your U naught is equal to small k sine cube pi x1 L. For the second question, my U naught is, that means the initial temperature is k Lx minus x square. And for the third question, my U naught is equal to your x when your length is from x to L by 0 to L by 2, and this is your L minus x when it is from L by 2 to L. So in this question I am solving these 3 particular cases. So if the rod of length, we have a rod of length L with insulated sides and with the initial temperature U naught equal to these 3 values for the 3 different questions. And if the ends are suddenly cooled, at 0 degree centigrade, then find the temperature uxt at any time t greater than 0. So we have a rod of length L whose sides are insulated, and for the first problem our initial temperature is this one and the ends are cooled at 0 degree centigrade. So we have to find out the temperature at any time greater than 0. For the second problem our initial temperature is changed, and again for the third problem it is your x when your x is between 0 to L by 2, and it is your L minus x when your x is between L by 2 to L. So let us solve first and second part, and third is similar to the first one. Second one. So solution for the first part. Solution of heat equation is, your solution is uxt equal to e power minus lambda square kt into a cos lambda x plus b sin lambda x. This is your solution of the heat equation with boundary condition. The first boundary condition is, when the length of the rod is 0, temperature is 0. Again, when the length of the rod is L, again we have given the temperature as 0 because the ends of the rods are at 0 degree centigrade. And the third condition is that the initial temperature is, that means the initial temperature is, for the first part it is your k sine cube pi x1 L. For second question it is k Lx minus x square, and for the third question it is your L, and your For the third question, it is your x and L minus x. So, let us use the first boundary condition. Now, u0t implies, that means when your x is 0. Now, if your x is 0, then sin 0 is 0. So, we have 0 equal to e power minus lambda square kt into a cos lambda x. So, from here you consider your a equal to 0. So, from here you consider your a is 0. If a is 0, therefore your uxt is equal to e to power minus lambda square kt into b sin lambda x. Now again use the second condition. Again ult equal to 0. So from here we have, now if your x is L, then your left hand side is 0. So we will have lambda square kt. Your a is 0, so b into sin lambda x. Now here you consider your b cannot be 0, otherwise the whole solution will be 0. That is not possible because temperature cannot be 0. So from here we will have sin lambda x equal to 0. That means it is equal to sin n pi. So from here you consider lambda equal to n pi. So from here sin lambda x equal to 0. So your x will be, your lambda will be n pi upon L, and your x is L. So this will be your n pi upon L. Therefore our solution is, therefore uxt equal to e to power minus k lambda square t into a is 0 into b cos b sin lambda x. And the general solution can be written as, therefore general solution is uxt equal to summation, b can be written as cn e to power minus k, your lambda is n square pi square upon L square into t into sin lambda, that means n pi x upon L. So this is your lambda is n pi upon L. So this is your solution of the problem. Now let us use the third boundary condition. In the third problem, now the same solution will be used for the second part. In the second part, again our two boundary conditions are, initial boundary conditions are the same. So this will be our solution for the second problem and third problem. And now what is your change? The initial temperature is changed for the all three questions. So for the first question, your ux naught is equal to k times sin cube pi x upon L. So if your t is 0, then here you can see that your left hand side will be k sin cube pi x upon L, and in the right hand side you can see that if your t is 0, so this will be e to power 0, that is your 1, and we will have n equal to 1 to infinity cn sin n pi x upon L. Now sin cube theta can be written as, because we know that sin 3 theta equal to 3 sin theta minus 4 sin cube theta. So your sin cube theta will be 3 sin theta. So your left hand side will be 3 sin theta sin pi x upon L minus sin 3 theta sin 3 pi x upon L into k by 4 equal to your right hand side cn sin n pi x upon L. So if you open the summation, then we will get c1 sin pi x upon L plus c2 sin pi x upon L sin 2 pi x upon L plus c3 sin 3 pi x upon L, and so on. So on comparing the coefficients on both the sides, you can see that your c1 will be 3k upon 4, c2 sin 2 pi x upon L, as there is no coefficient of sin 2 pi x upon L in the left hand side, so c2 will be 0, and your c3 will be, that means the coefficient of sin 3 pi x upon L will be minus k upon 4. Therefore, and all the other remaining constants are 0. So from here your solution will be, therefore our answer is C1. C1 means 3k upon 4. That means when your n is 1, into e power minus k pi square t divided by L square into sine pi x upon L. Then C3 is minus k upon 4. When your n is 3, that means your 9k pi square t upon L square into sine 3 pi x upon L. So this is your solution of the problem. This is your solution of one-dimensional heat equation. Now let us solve the second part. So this is your answer. For the second part, because the boundary conditions are same, so this will be your solution. Solution of heat equation is, up to this step we have all the things common, so your ux will be Cn into e power minus k n square pi square t is upon L square, then sine n pi x upon L. So this will be your solution. Now our boundary condition is changed. So because your initial temperature is equal to, your initial temperature was k Lx minus x square. So therefore, if t equal to 0, then we will have in the left hand side we will have k Lx minus x square, and in the right hand side we will have Cn into sine n pi x upon L. Sure. Now you can see that this is your half range. Now this is your half range sine series. If this is your half range sine series, then the coefficient Cn will be 2 upon L, 0 to L, into your fx. Fx is k Lx minus x square into sine n pi x upon L dx. So this is equal to 2k upon L, 0 to L, Lx minus x square into sine n pi x upon L dx. Now let us use the Bernoulli rule of integration. So this is equal to 2k upon L, then this will be your 2 Lx minus x square, then integration of sine will be your minus cos n pi x upon L into L upon n pi, then we will have minus sine, then we will have minus sine. Now the differentiation of this term will be L minus 2x. So now the integration of this bracket will be minus sine n pi x upon L divided into L square upon n square pi square, then we will have plus sine, and the differentiation of this term will give you minus, so this will be a plus, and again integration of sine will be a cos, so we will have cos n pi x upon L into L cube upon n cube pi cube, and the limits from 0 to L, and we will have the limits as 0 to L. Now here you can see that if your x is L, then this term will be 0 because we will have L square minus L square. Again if x is 0, then this term is 0. So the first term is 0. In the second term, if your x is L, then we will have sine n pi, that is your 0. Again if x is 0, we will have sine 0, which is your 0. So only the third term will get survived, and for that, therefore it is equal to 2k upon L. Now this term is 0, this term is 0. From here we will get minus 2 into L cube upon n cube pi cube, then we will have cos n pi minus cos 0 is 1. So this is equal to 2 to the power 4 times k L cube. Now this will be your L square upon n cube pi cube into 1 minus 1 power n. Now you can see that if your n is odd, then this will be your, now if your n is odd, then this will be your 2 times, and for the rest cases it will be your 0. So this is your, if n is odd, and for the remaining cases it is 0. So now your solution will be that the solution of the heat equation is equal to uxt equal to Cn is 8 kl square upon n cube pi cube if your n is odd, and into e power minus k n square pi square t upon l square into sin n pi x upon l. So this is your required solution. And the third part is again similar to the second part, so I am not going to in the third part. You can solve it in a similar fashion as we have done the second part.